In this section, we will continue to investigate trigonometric or polar form of complex numbers. We will learn how to find powers and roots of complex numbers. Hello, my name is Tom Atwater. Let's start by reviewing Drogs Theorem. If r times cosine theta plus I sine theta is a complex number, and if n is any real number, then r cosine theta plus I sine theta, all raised to the power of n, is equal to r to the n times cosine n theta plus I sine n theta. In compact form, this is written r cis theta, all raised to the n, is equal to r to the n times cis n theta. Let's go right to an example to illustrate the theorem. Find the quantity 1 plus I square roots of 3 all to the 8th power and express the result in rectangular form. So, of course, we could take that binomial and raise it to the 8th power in its rectangular form and have to FOIL 8 factors. But of course, it's much easier using the polar form. So the first thing we want to do is take that 1 plus I radical 3 and convert it to its polar equivalent, which would be 2 cis of 60 degrees. And I'm assuming that you all remember how to make that conversion. And that's important for this lesson because after we raise this to the 8th power, which is our next step, we will do that and then convert it back into rectangular form. So, taking 2 cis 60 and raising it to the 8th power means taking 2, raising it to the 8th power, and then multiplying 8 times the 60-degree angle. And now let's expand this. 2 to the 8th is 256. Then we would have cosine 480 degrees plus I sine 480 degrees. So, now evaluating the cosine of 480. Of course, subtract 360 from that and we're left with 120. So we're looking at the angle of 120, which of course is in quadrant 2, and it has a reference angle of 60. Well, the reference angle of 60 is good, but then we need to remember that cosine is negative in quadrant 2. The sine is positive in quadrant 2. So what we have next is 256 times negative 1/2, because the cosine of 60 is 1/2 negative in quadrant 2, plus I times positive the square root of 3 over 2. Now we have to distribute the 256, which will give us an answer of 256 times negative 1/2 for negative 128 plus 256 times I radical 3 over 2 leaves us with 128 I times radical 3. Okay, now we want to look at Drogs Theorem and extend it to what's called the nth root of complex numbers. Let's look at this. If n is any positive integer, r is a positive real number, and theta is in degrees, then the non-zero complex number, r cis theta, has exactly n distinct nth roots, given by the nth root of r times cosine of alpha plus I sine alpha, where alpha is equal to theta plus 360 times k, all divided by n, or the form for alpha that we typically use is alpha equals theta divided by n plus 360k divided by n, where k is equal to 0, comma 1, comma 2, all the way up through n minus 1. Well, let's do an example of finding the roots of a complex number. So here we are, find the 2 square roots of 4i. Write the roots in rectangular form. So the first thing we need to do is convert 4i to its polar form. And recall 4i in polar form is going to be 4 times the cosine, cis of 90 degrees, or let's do it as pi over 2, just to do it in radians compared to our first example. Therefore, of course, we know that r is equal to 4, theta is equal to pi over 2, and the modulus that we're looking for is the square root of 4, which is 2. So therefore, we start with alpha, and that's going to equal the pi over 2 divided by 2 plus 2 pi k divided by 2. And we have k equaling 0, k equaling 1, and k equaling, oh, that's it, just k equaling 1. Getting ahead of myself. So now we have to figure out what alpha is equal to for k equals 0. So let's simplify this a little bit. Pi over 2 divided by 2 would give us pi over 4. Plus, simplifying this, we get pi k. And so now when we plug 0 in for k, this becomes 0, and we're left with pi over 4 for alpha. What about for k equals 1? We plug in 1 for k times pi is pi, plus pi over 4 gives us alpha equals 5 pi over 4. So now our polar form for these roots would be 2 cis pi over 4 and 2 cis 5 pi over 4. But what about the rectangular form for those? Well, the rectangular form would be the square root of 2 plus I square roots of 2, and we would have negative the square root of 2 minus I square root of 2. So there we have both the polar and rectangular roots for the square root of 4i. Let's try an example which finds the fourth root of a complex number. Find all fourth roots of negative 8 plus 8i square roots of 3. Write the roots in rectangular form. Once again, the first thing we're going to want to do is change it to its polar equivalent. So take negative 8 plus 8i square roots of 3. And that's equal to, in polar form, 16 cis of 120 degrees. Now, in this case, we're looking for the fourth root. So the modulus that we need is the fourth root of 16, which of course is 2. So therefore, we have that alpha is going to be equal to 120 divided by 2 plus 360k divided, I'm sorry, not by 2, by 4. and 360k divided by 4 because we're finding the fourth root. All right, now we have k equals 0. And again, let me simplify this. This, of course, reduces to 30 plus 90k. And that's going to make it a little bit easier for us. K equaling 0, 90 times 0 is 0. We get alpha equals 30. What about for k equals 1? For k equals 1, we get alpha is equal to 90 times 1 plus 30, 120. What about for k equals 2? For k equals 2, we get alpha equals 2 times 90 for 180, plus 30 is 210. And finally, for k equals 3, we have 90 times 3 for 270, plus 30 for 300. So alpha is 300. And each of these are in degrees. So now, for the polar form, we have 2 cis 30 degrees, comma, 2 cis 120 degrees. We have 2 cis 210 degrees, and we have 2 cis 300 degrees. Well, what about the rectangular form? The rectangular form, move over because I've run out of space, we're going to have the square root of 3 plus I, comma, then we would have negative 1 plus I square roots of 3, comma, then we would have negative the square root of 3 minus I, comma, and then finally 1 minus I square roots of 3. Well, now it's time for you to try an example. Find the cube roots of 64i and write the roots in rectangular form. Pause the video to work on this problem. When you're finished, restart the video to check your solution. Welcome back. Let's find out how you did. The first thing we want to do is convert 64i into its polar form, which would be 64 cis 90 degrees. And now we want to find the cube roots. So the modulus is the cube root of 64, which is 4. And our alpha is going to be equal to 90 degrees divided by 3 plus 360k divided by 3, which is equal to 30 degrees plus 120 degrees k. We have k equals 0, 1, and 2. And plugging those in, 0 times 120, of course, is 0, so that tells us that alpha is 30 degrees. What about k equals 2? Well, I'm sorry, k equals 1. 1 times 120 is 120 plus 30 is 150. Alpha equals 150. And finally, for k equals 2, we get 240 plus 30 for 270 for alpha. So our polar form for the roots would be the 4 cis 30 degrees, comma, 4 cis 150 degrees, comma, 4 cis 270. If we put them into their rectangular equivalents, we get 2 square roots of 3 plus 2i, comma, negative 2 square roots of 3 plus 2i, and of course, 4i. I'm sorry, negative 4i. Negative 4i. All right, great job. Let's try solving an equation by finding complex roots. Find all the complex solutions of x to the 5th minus 1 equals 0. Graph them as vectors in the complex plane. So the first thing we'd want to do is write x to the 5th minus 1 equals 0, which means x to the 5th equals 1. So we're looking for the 5th roots of 1. 1, when we convert it from its quote-unquote rectangular form to polar form, would be 1 cis 0. And the modulus, of course, is the 5th root of 1, but the 5th root of 1 is, of course, 1. Alpha, then, alpha in this case would be 0, well, over 5, but that's just 0, right? Plus 360k over 5, which means it's just 72 degrees times k. And we have k equals 0, 1, 2, 3, and 4. So for k equals 0, we get alpha equals 0, because 0 times 72. What about for k equals 1? We'll just get 72 times 1. Alpha equals 72. Then what about k equals 2? K equals 2, 72 times 2, for alpha equals 144. For k equals 3, we get 3 times 72, so alpha is going to equal 216. For k equals 4, we're going to get that 4 times 72, or alpha equals 288 degrees. So now I can write out all of my polar forms, but I've run out of space again. So let's move over and write the 4 polar forms of that, which would be, of course, 1 is our modulus, so we don't need to write that. We would just write cis of 0. We'd have cis of 72. We'd have cis of 144. We would have cis of 216. And we'd have cis of 288 degrees. We were asked not to put them in rectangular form this time, but to graph them. So let's take a look at what that is. All right, so we have the 5 vectors, and just to make it clear, we have this vector right here along the x-axis, which represents our cis of 0 degrees. And that's the expanded form for it. And then we have the other 4 roots in their expanded form, the cis 72, cis 144, cis 216, and cis 288. All right, that was fabulous. Now, in this lesson, we learned and investigated trigonometric or polar form of complex numbers to learn how to find powers and roots of complex numbers. We used Drrogs Theorem and the nth root theorem. Be sure to work the exercises that your teacher assigns, and we'll see you next time.